Two particles with equal charge magnitude 2.0 times 10 power minus 7 coulomb, but opposite signs are held apart. What is the magnitude and direction of the electric field E at the midway between the charges? So try to make a diagram according to given information. So two particles with equal charge magnitude. So take two charges. One is negative charge and another one is positive charge, because they both are equal and opposite magnitude. They are separated at a distance of 15 centimeter. 15. They are separated at a distance of 15 centimeter. Now, what is the magnitude and direction of electric field at the midway between the charges? So our task is to find out the magnitude and direction of the electric field at the midpoint. So if you take, so this is the distance between them as R, a point P exactly at midpoint P. So at this point, so we will find out the magnitude and direction of the resultant electric field. Now, to do further solution, just I am taking an assumption that the distance between them equal to, instead of the 50, I would assume let it as x. The distance between them equal to x, and the point P exactly the midway. It means from this point this distance goes to x by 2 and here also goes to x by 2. Since I need to find out electric field at point P, let me take as this positive charge 1 and this as charge 2. I wish to find out electric field due to positive charge. So electric field due to the charge 1 at P equal to, according to Coulomb's formula, according to electric field, so it's force per unit charge. You can cut it out everything, so you can get it that value K times, here the source charge is only the positive, K times Q by R square. So here the R square equal to x by 2 whole square. And electric field at a point P due to second charge. So the electric field at a point due to 2 at point P equal to K times, here the magnitude of the charge equal to, since it's the minus Q, so we can take, remember carefully again, minus gives about the direction, so I will drop the minus sign there. So for time being I will take, so minus Q times x by 2 whole square. So this sign tells about direction. So by symmetry, if you can see the magnitude of the electric field, so the magnitude of electric field due to charge Q, due to the first charge at P equal to the magnitude of electric field due to second charge at P. Since these two magnitudes are the same, so total electric field at point P, total electric field at point P is nothing but electric field due to the first charge plus electric field due to the second charge at P. So if you can take the modulus value of that ones, so you can take only the modulus values, you can give the modulus to everything for the magnitude. So these two values will be add up. Electric field at point P equal to K times and the Q by X by 2 whole square, its magnitude, plus here also K times Q by X by 2 whole square. So this is also magnitude. So electric field magnitude. So which gives this, you can sum up. So K times, sorry, it's not the whole square, it's only the X by 2 square. It's the denominator square. We can get the value 2 times K Q by X by 2 square. Now the problem becomes easy. Now we are having all the values. You can substitute those values to get the result. K value 2 times K value 9 times 10 power 9 and charge Q equal to the magnitude of the charge equal to 2 times 10 power minus 7 coulomb divided by X. Here the X is 15 centimeter. You can convert that in terms of the meter and divide by 2. You can get the value is that 0.7075 meter square. Since we have to deal everything with the meters, so X value is 15 by 2, 0.75. Again you can divide with this in terms of to convert in terms of meters, you will end up with that values. Now if you can do this calculation, so the result you can reach the electric field at point P, the magnitude of electric field at point P equal to 6.4 times 10 power 5 Newton per coulomb. So this is the magnitude of the electric field at point P. Now where is the direction? Now where is the direction? To represent the direction, either you use standard notation or it's better to use vector notation. So if you remember the vector notation, if you take x-axis, this is the negative x-axis and this is the positive y-axis and the negative y-axis. Along the positive x-axis, the unit vector we will take I cap, and along the negative x-axis, the unit vector we will take as minus I cap. Now, can you guess where would be the resultant electric field? To know the direction of the electric field, we need a help of test charge. Now, at a point P, if I bring a positive test charge, it is a standard convention. If I bring a positive test charge at point P at here, since it's positive, the resultant electric field is along in this direction due to plus Q charge. And if I bring a positive test charge at point P at here, due to the negative charge, a negative charge here and the positive charge here, so that is also due along in this direction. Remember carefully, if I bring a positive test charge, that's the one way to know the direction of electric field. If we bring a positive test charge at point P, so from charge due because of charge 1 and because of the positive test charge, so they repel. So this is the resultant electric field direction. And due to the negative charge at P, the electric field also in the same directions, and they both are showing towards to negative x-axis. So I can say the electric field direction, the direction of the electric field is along, the direction of electric field is along negative I cap. So the magnitude and the direction of the electric field is the magnitude and the direction of electric field. The magnitude and direction of electric field equal to 6.4 times 10 power 5 Newton per Coulomb along I cap, sorry, negative I cap. So how would we know the direction? To know the direction at that point, we need to bring a positive test charge. That positive test charge shows the resultant electric field direction.